Okay, ladies and gentlemen, let's go ahead and finish up section 1.5. What we're asked to do here is to list four ordered pairs that belong to the relation determined by the equation listed below. The first relation I'm given is A equals 9 minus t squared. Now, very important thing to notice there. Since A is alone, in other words, A equals, A represents your output. T is on the other side of the equation, which involves some computation. That represents your input. So the first thing you should notice in my columns here, T goes in the first column, A goes in the last column. Input goes first, output goes last. Now, since T is the input, I need to make up values for T. So I've chosen, it gave me carte blanche here. I've chosen the numbers 0, 1, 2, and 3 simply because those are very easy to work with. Let's start with 0. If I replace t with 0, 9 minus 0 squared becomes 9. So my first ordered pair would be 0, 9. If I replace t with 1, 9 minus 1 squared becomes 9 minus 1, which is 8. So my next ordered pair is the ordered pair 1, 8. And so on. If I replace t with 2, 9 minus 2 squared is 9 minus 4, which results in 5. So I have the ordered pair 2, 5. And finally, if I put a 3 in the place of t, 9 minus 3 squared is 9 minus 9, which is 0. 3, 0 is my last ordered pair. I'm going to answer the next question, which says, how many ordered pairs could you have listed? I hope you understand the answer is infinitely many. And of course, the reason is we could have gone on all day. We could have kept naming other values for t. So this relation has infinitely many solutions. Okay, our next relation is fractional. Z equals 1 over m squared plus 3. Now again, Z is alone, which means that's the output, so it goes in the second column. M is the input. By putting a number in for m, you get out an answer for z. And again, I've chosen logical values for m. 0, 1, 2, 3, they're all very easy to work with. When I put in a 0, on the bottom I have 0 squared plus 3 is 3, but don't forget we still have a 1 on the top. That's why we have the answer for z as 1/3. So it's the ordered pair 0, 1/3. When I plug in a 1 for m, 1 squared plus 3 is 4 on the bottom, but there's still a 1 in the top. That's why I have the answer 1/4 for z, so that ordered pair would be 1, 1/4. When I plug in a 2 for m, 2 squared is 4, 4 plus 3 is 7, thus giving me the answer 1/7, so we have the ordered pair 2, 1/7. When I plug in a 3, 3 squared is 9, plus 3 is 12, thus giving me the answer 1/12 as a complete answer. So it's the ordered pair 3, 1/12. How many ordered pairs could we have listed? Again, infinitely many. Our last question here asks us to plot the points 0, 1, 1, 2, 2, 3, 3, 4, and negative 1, 2. Okay, 0, 1 is on the y-axis. 1, 2 is in quadrant 1, 2, 3 is in quadrant 1, 3, 4 is in quadrant 1, and then negative 1, 2 zaps us over to quadrant 2. Why does this picture represent a finite relation? The reason, you can count how many points you have. 1, 2, 3, 4, 5. It stops. The domain of the relation is an integer x such that, okay, you have a blank less than or equal to x less than or equal to and another blank. X is the letter we use for domain. The way I teach my students to find domain is I tell them to scan from left to right. So, when they look at this graph and scan from left to right, the leftmost x value is negative 1. I continue scanning and the rightmost x value is a positive 3. So we put negative 1 in the first blank, we put 3 in the second, and that's basically telling me that the domain is any integer between negative 1 and 3. The range of a relation, when I tell my students how to find range of a graph, I tell them to move from bottom to top. So, what we're going to do is we're going to start at the very bottom of the graph. The bottom of the graph is the y value of 1. When I go to the very top point in the graph, the value is 4. That's why my range is an integer between 1 and 4. So the way that's written, 1 is less than or equal to y is less than or equal to 4. Okay. Other than for my email popping up, we should be done.